In this next section, we're going to be talking about the biological effects of radiation. This is section 41.4. And this is very important for anyone in the medical sciences or biological sciences, because you're interested in knowing from all of these radioactive effects, how do they affect living things? And that's the biological effects. And you need to know that the Earth is radioactive. I mean, if you just dig up dirt, you've got radioactivity. And the soil is radioactive. We have radon, which is a threat, which is a radioactive gas that comes out of the soil that actually causes cancer to a lot of people. They don't understand where this radon comes from, but it comes out of the ground. It comes from a disintegration of radioactive materials, and it bubbles up and it gets in your house or it gets in your well for your drinking water, and you can drink it, and it's very carcinogenic. So we need to understand these biological effects. I will warn you, however, in this section, there are just more units in here than a person can remember. It's a difficult section because there's so many units measuring radioactivity because the biological effects are so complex. So let's start out and look at what happens when radioactivity comes through your body, or the body of anything, any living thing, a mouse or a frog or anything. Well, as this radiation comes through, it's either a charged particle or a gamma, and it knocks electrons from the atoms and it damages the cells. So the cell is damaged or made useless by this radioactivity. It can even be altered in its chromosome structure. Now, the SI unit of ionizing radiation is the Coulomb per kilogram. Coulomb per kilogram, okay, that's standard notation. That's the SI unit for ionizing radiation. In other words, if we have some radiation on a kilogram of living material, then the unit of that radiation is going to be knocking out 1 coulomb of electrons from the cells. 1 coulomb for each kilogram that's there. And that's our SI unit. But we're going to have a lot more units than that. The more common historical unit is the Roentgen. The Roentgen is actually 2.58 e to the minus 4 coulombs per kilogram. Of course, I don't expect you to remember these numbers, but you need to remember that they exist, and this is called the Roentgen. It's named for the man, Roentgen. And it was a more common historical unit back before we were using the SI units for everything, and it had a different source. You can see it's smaller. It's about 1/1000th or 1/3000th of the amount that you have here. So we can talk about a Roentgen of ionizing radiation. That means you would have less charge knocked out of a kilogram of living matter. Now we can talk about an absorbed dose. An absorbed dose is how much energy we absorb divided by the mass that we have absorbing it. So it's energy per mass that's absorbing it. So how much energy do we absorb? It's a lot more meaningful. And this is called a Gray, G-R-E-Y. The unit name is GY. And it is a joule per kilogram. You can say, well, I can understand how this is a reasonable unit. Back here we're looking at how much charge is knocked out, but here we're looking at how much energy is absorbed in joules per kilogram, and that's called a Gray. You need to certainly remember a Gray, and you certainly need to remember this SI unit here, but it doesn't have a special name. The Roentgen is, you do not have to remember what this value is, but remember that it's in terms of charge per kilogram. Next, we have something called the radiation absorbed dose. And this is a common unit. It's 1/100th of a Gray, because a Gray is pretty large. So this is a rad. and many of you have heard of rads. Oops. RAD, and a rad is 0.01 of a gray. That's more common. Many of you in the medical sciences will have heard of a rad of radiation. Now, yeah, there's a lot more. If we want to compare the damage from different types of radiation, we can define the relative biological effectiveness. That's called the RBE, relative biological effectiveness. And it is how much damage do you do compared to a dose of 200,000 electron volts of X-rays per your dose. In other words, how many of these doses do you have per your dose? And that's the dose of 200 keV gammas to your dose. And that's relative biological effectiveness. It's how damaging that is, and it compares it to a gamma ray. So you have more of a standard, because you see the beta rays, your alphas, your gammas, your neutrons, all of these do different things to your body. So you want to kind of get these into kind of common units, which you do here. Then you can talk about biologically equivalent dose. And a biologically equivalent dose, this is in terms of REMS. The REMS are the absorbed dose in rads times the relative biological effectiveness. REM stands for Röntgen equivalent man. This is for a man. This is Röntgen. I probably should write this down here. That's what a REM is. I know I got off the page there. But a REM is a Röntgen equivalent man, and it's your dosage times the biological effectiveness of that dose. That should be RBE, relative biological effectiveness of that dose, and how damaging it is. Now let's go to humans and see what happens with humans and so forth. I believe I can see that on this page. I'll just have to turn this over so we can get to it. So now we're talking about REMS, and REM is a Röntgen equivalent man. It's your absorbed dose in rads times your relative biological effectiveness. And the relative biological effectiveness is equivalent to a dose of 200 keV X-rays. Kind of getting kind of complicated. But humans receive an average dose of 360 millirems per year from all sources. From all sources. So this is how much you're going to get. Every year, you're going to get about 360 millirems. It's important to understand where that comes from. Out of your 360, about 28 comes from cosmic rays from outer space. About 28 comes from the Earth, because the Earth is radioactive. Your body is radioactive, so you get 39 from your own body. Your body is radioactive, radiating your own body. That's something most people don't know. Wow, radon, you heard me mention it a while ago, 200. This is the gas that bubbles up out of the ground, that's invisible, tasteless, and odorless, comes into your house, into your basement, into your well water, and it's a gas that's easily dealt with if you know what you're doing. But 200 is a lot, and some people get a lot more than that. Like in a farm, if you're using well water, you need to know how to get rid of that radon. You merely let the water sit for a while. The radon will go off the top. If it sits for a day or 2 or 3 days, the radon will go out the top of the water, and it's perfectly safe. And your medical and dental are about 43. That's your X-rays and things like that. Now, the general population should not get more than 500. You see, the average is about 360. So you'd say 500 should be a maximum for a regular person during a normal year. And this is in milli-thousandths of rems for each year. Now, workers who are in the medical profession, working with radioactivity and everything else, like dental assistants, should not get more than 5 rems a year. Ooh, that's a lot more, isn't it? 5 rems is not millirems, so that's 5,000. So 5,000 is a maximum of, this is regular humans. These are workers. A worker should not get more, must not get more than 5,000 millirems, or 5 rems per year. And that would be something like a dental assistant might get. So this gives you some rough feeling for these different units in radioactivity, and you need to be familiar with all of these.